All right, congratulations. You've made it to the last day of notes for this unit. So we're still talking about conservation of momentum, and we're still talking about collisions, but now we're going to look at what happens during a collision when the two objects don't stick together, they bounce. So we talked in the last notes that during a collision, momentum is still conserved, and that's going to still hold true. So momentum is still conserved. Which means that the initial momentum has to equal the final momentum of the system, because there are no F net external is equal to 0. So one thing we have to be careful about here is we have to be very careful with your signs for your velocities. It's really easy to get these problems wrong if you assign the wrong sign for velocities. And we talked about elastic versus inelastic last time as well. So momentum is conserved. You want to be careful with your signs. Remember, elastic means that kinetic energy final is equal to the initial kinetic energy. Inelastic means that the kinetic energy final is less than the kinetic energy initial. In both of these cases, we can find that the object bounces. So in a perfectly inelastic collision, and we say that it's perfectly inelastic because the two objects stick. In a regular old generic elastic collision, they bounce. In an elastic collision, the objects bounce. So how do you tell the difference? You have to determine which is which by looking at the kinetic energy. Okay, to determine if the collision is elastic or inelastic. Okay, so we're going to do some of that today. Now, if you ever come upon a problem and you find that the kinetic energy final is greater than the initial kinetic energy, you probably made a mistake. So go back and check your work, because that should not happen. A couple other things about kinetic energy. Sorry about the bell there. A couple things about kinetic energy. Remember from our unit last semester, kinetic energy is equal to 1/2 times mass times velocity squared. That's kind of our general equation. Remember, mass has to be measured in kilograms. Remember, velocity has to be measured in meters per second. And then energy is measured in joules, capital J. It's always going to be a capital J, okay? Now, the other thing that people sometimes make a mistake with is that they try and lump things together. So you can't just say, oh, well, I've got to find the total kinetic energy for the system. You can't say, well, kinetic energy is just 1/2 the total mass times the velocity total. That's not going to work. You have to look at each individual object. I'm struggling with the bells here, obviously. Okay, so you have to look at each individual object. So if you have two objects, the total kinetic energy for those two objects is going to be 1/2 the mass of object 1 times the velocity of that object squared, plus 1/2 times the mass of object 2 times the velocity of that object squared. Don't just add the masses and the velocities and do some kind of funny thing there, okay? All right, so let's go ahead and let's try a problem. And the first thing we're going to do is read it, and then we're going to draw it. So we have a 2-kilogram cart moving at 0.5 meters per second on a frictionless track, and it runs into a motionless 3-kilogram cart. So I'm going to go ahead and I'm going to draw this. So here is my cart, and I'm going to call that cart number 1. And it's moving along, and I'm just going to go ahead and I'm going to put right there that it's 2 kilograms, and that it's moving at 0.5 meters per second. And it says it runs into a 3-kilogram cart, so I'm going to draw that a little bigger, whose velocity is 0. So this is the initial condition. And then bam, they run into each other. Okay, so here is my 2 kilogram cart. And here is my 3 kilogram cart. And it says, the problem says, the 2 kilogram cart bounces back at 0.1 meters per second in the opposite direction. That means it's going in the opposite, it was going to the right, now it's going to the left. And its velocity now, you're probably going to want to put 0.1 meters per second. But remember the signs. Since it's going backwards, it's got to have a negative velocity now. Still have my 3 kilogram cart. I don't know. I know that it's going to be moving to the right, right? I hit it to the right. I exerted a force on it to the right. I know it's not an external force, but it's an internal force. So I have a feeling it's going to be going this way. So I'm going to call that V2 final. Now I'm going to go ahead and I'm going to remember conservation of momentum. P initial is equal to P final. And this is going to be a little tougher to write because this is all you're going to get from your equation standpoint, but I have to find the initial momentum of these carts together. So their initial momentum is going to be mass 1, velocity 1, and its velocity initial, mass 2 times velocity 2 initial. And that's going to equal the final momentum, which is going to be mass of object 1 times the final velocity of object 1 plus the mass of object 2 times the final velocity of object 2. And then I'm going to plug in what I know. I called this object right here object 1. I'm calling this object 2. So I've got 2 kilograms times 0.5 meters per second plus 3 kilograms times 0. Well, that's nice. That goes away. Must equal 2 kilograms times negative 0.1 meters per second. Make sure you include that negative sign. Plus 3 kilograms times V2 final, which I don't know. But I think I can go ahead and I can do some math and I can come up with the correct value for V2 final. So let's see, 2 times 0.5, that's 1 kilogram meter per second, must equal negative 0.2 kilogram meter per second plus 3 kilograms times V2 final. Go ahead and do a little algebra there and you should be able to come up with the correct answer. When I bring over that 0.2, I should get 1.2 kilogram meters per second equals 3 kilograms times V2 final. You should see that V2 final is equal to, the kilograms cancel out, it should be 0.4 meters per second. Now, if we asked if the collision was elastic or inelastic, now is when you would go ahead and you would find the initial kinetic energy for the system and the final kinetic energy for the system. So let's go ahead and let's do that now. Give myself a little more room. So let's, I'm going to change color here. Let's find the initial kinetic energy. The initial kinetic energy is going to be 1/2 mass of object 1, V1 initial squared, plus 1/2 mass of object 2, V2 initial squared. But I know that the initial velocity of the second object initially was 0, so I can get rid of that. So my initial kinetic energy is 1/2 times 2 kilograms times 0.5 meters per second. That has to be squared. And I go ahead and plug that in your calculator. You should find that the initial kinetic energy is 0.25 joules. Great. Now let's go ahead and let's find the final kinetic energy. So the final kinetic energy is going to be 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. That's going to be 1/2 times 2 kilograms times negative 0.1 meter per second squared plus 1/2 times 3 kilograms times 0.4 meters per second squared. Now be careful with your math here. When you square this negative 0.1, this negative goes away. Don't plug it in your calculator incorrectly and get a negative number. Whenever I square a negative number, I get a positive number. Okay, so be very careful with your calculator there. So go ahead and you throw that in your calculator. You should find that this is going to be 0.01 joules plus 0.24 joules, which turns out to be 0.25 joules. You should notice that the initial kinetic energy is exactly the same as the final kinetic energy, which means then, since kinetic energy initial equals kinetic energy final, this was an elastic collision. The problem didn't ask for that, but I wanted to show you how to do that anyway. Okay? That's it for today. You've got some problems to work on. Good luck with those, and see you in class.